In the last lecture, we did something called what we did.
Derivated the current problem and branching the rest of the problem.
Yeah, we did different types of circuit, right?
Yes, sir.
Yeah.
So I think circuit part is over. We have done the grid problem also, and okay. So now there is something called delta star method. So that method I can teach you in either current or you can learn here also. Okay, let me do it here only. So we read as delta star, but we write as delta y. The y is read as star. Okay. Now this method is the ultimate, the last resort if you come across a circuit and you're not able to figure it out that how to solve it. Then this is the only way to go ahead. So if there is no simplicity, if nothing is there, then this becomes really useful and it helps in solving the question. So what is delta? So delta represents 3 branches of circuit. And this 3 branch can be present anywhere in the larger circuit. So we are not trying to show it the exact circuit. Imagine some sort of 3 branch configuration. You can see somewhere in the circuit, not exactly this is the circuit, it is somewhere present. So if this circuit is present somewhere, and let's say each branch contains 1 capacitor, or if this is the equivalent capacitance of each branch, and if I call this is A, B, C are called junctions. So we have 3 junction A, B, C, and between every pair of junction we have some capacitance. So let's call C1, C2, and C3. And the remaining part of circuit is not shown to you. It is shown by the dashed line. Now what is star or Y? So in the theory of transformation of circuit, when you transform one circuit into another form, the theory says that the junction must be maintained. We cannot affect the junction. So A must be there, B must be there, C must be there. And at the same time, the equivalent capacitance between the circuit and its transformed version must be equal. So what does it mean? If I create a Y shape like this, pretty much inverted Y shape, the 2 circuits must exhibit similar equivalent capacitance value. And when we do so, we call it the transformed circuit of the given circuit. So the delta converts into Y form and Y can be converted into delta form. Okay. So let's call this as CA. So imagine C1, C2, C3 is given to you and you wish to transform into a Y form. But while doing from delta to Y, we have to choose a new set of values of CA, CB, and CC. And these values are chosen in such a way that the equivalent capacitance between any 2 terminal or any two junction remains unaltered. So right now we are not going to consider the other branch or other part of circuit. We will assume only these three capacitor as the capacitor present. And what we try to do is we try to equate the equivalent value between any two branch in the two circuit. So that is a thumb rule of transformation. So for terminal A and B, what is the equivalent capacitance in the delta format? So if you choose A and B as your terminal, then other we have to ignore, so others are not present. So tell me what is the C equivalent capacitance between A and B. So you have to choose A and B as terminal. And if you solve, what will you get the answer? So for A and B, we can see 1 and 2 are in series,
Yes.
which in turn in parallel with the A and B, correct?
Yeah.
So can we write
C2, C1
C1,
upon
C2?
And C1 plus C2
plus
plus
C3.
But if you try to do the same thing in the Y transformational circuit, what is the C equivalent between A and B? If I choose this as terminal, then the equivalent will be only these two in
CF,
series.
yes.
But CB will it will be of no use, right?
Yes.
Yeah.
So we can write as CA, CB, CC. No, yeah. CA, CC upon.
CA plus C.
If you look at the left hand side and if you try to take the LCM, you will get something called 1, 2, 1, 3, 2, 3. And you will get here 1 by CA. So similarly, you can do it for the other terminal. So for terminal B and C, what we can write on the delta form and what we can write in the star form. So in the delta form, what we can write?
C2 C3 by C2 plus C3
Plus C1.
So for B and C, I can see it's a C2 C3 upon C2 plus C3 plus C1, right?
Yeah.
On the RHS, we can write as CBCC
yes CP plus CC.
plus CB plus CC, correct? And if you rearrange, you can again see we are approaching towards some sort of definite pattern. So if I choose the question 1 and this is a question 2, okay, so what we are going to do is, okay, let's start the third part. So for A and C. So for A and C, quickly tell me the answer.
C1 plus C. Yes. CA, CB upon CA plus C.
All right. Now the next step is, okay. So this will also have the pattern C1, C3. Now what you can see that the pattern is very much obvious. The numerator on the LHS is same for all, right? The numerator of the LHS for every question is same.
Yes.
Yeah.
So what we are going to do is we are going to invert all equation. So if you invert all equation, so what I'll do is C1, C2, C2, C3. I'll write this as summation Ci, Cj. It's a notation, shortcut notation to write the consecutive product. It's easy to write, nothing else. Now, invert all equation. So if I invert the first equation, it will give you 1 by Ca, 1 by Cc, right, on the RHS.
Yeah.
The RHS becomes interesting. So it is 1 by equation 1, 1 divided by equation 1 implies, and what you get here is 1, 2 upon Ci, Cj. In shortcut, I don't want to write again. 1 upon equation number 2 will give you what? 1 by
C
B, 1 by
plus-
C. Yeah. 1 by B, 1 by C, and the numerator is how much? 2, 3 upon summation. In fact, I can just write summation. Okay, no, that's too much. And 1 by equation number 3. AC, BC, whatever left with
AB.
AC. AB, yeah.
AB.
AB, very good. 1, 2, 2, 3, so 3, 1. So now we have the equation number 4, 5, and 6. So what we can do here? 4 plus 5 plus 6. Add all, because if you add, it's a really nice pattern. You can get a twice of each value, 1 by C. On the RHS, you will also get something really nice. C1, C2 plus C3 2 times each, right?
Yeah.
Yes.
So basically, so now you're done because we have the very nice answer. So what we have to do is subtract 7. So 7 minus 4, 7 minus 5, 7 minus 6. You get all answer. So 7 minus 4, how much? A and C is gone. 1 by B.
Only. And 3.
And 1, 2 is gone. So C3 by summation.
Yes.
So, okay, we got the answer. What is CB? CI, CJ upon C3. What is 7 minus 5? BCA,
A.
right? And 1? So what you can see that we can derive the transformed value if we know the delta. So if you know the delta, can find the star and 7 minus 6. Now, if this is taking so much time, how we can use the in the examination? So definitely we have a pattern. So there must be some neat way of getting it without doing all this calculation. And the answer is yes, we can get the value very easily. How? So numerator is the consecutive product of two capacitance AB, BC, CA in the delta format. So let me do the delta format in a large scale like this. And inside the delta, try to draw the star. This was A, correct? This was the ABC assumption. Okay. 1, 2, 3. CA. So now how to find CA? So you can see the capacitance in front of CA is which one?
C1.
C1.
And CB?
C2.
Check the answer. For B, we are getting 3. How it is possible? I have made a mistake. For B and C, it is the first was A and C. C. So that will be B. 1, 2. Just 1, 2. It should have in sequence CA is getting C1, that's correct. B should get C2 and okay, I think I have made a B, C2 and C is 3. A, C. 7 minus 4, 1 by C. Some mistake has happened, just let me check. For A and B, the answer is 1, 1, 2, 1 plus 2 plus 3. And for A and B, it is C, 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 C. Something's wrong. For B and C, B, C, like this. Ah, So see the mistake.
I think you wrote the name wrong.
Yeah, that's right. I've changed this
Yes.
name. This is B and this is C. Oh, so that's what the mistake was, because A and B must have A and B only, na? That's logical. And for B and C, it should be B and C. That's okay. That's written correctly. Okay, luckily B and C is correctly. Okay. And for C and A, this will C. Okay. Okay. So now we can get the correct answer. This is A and B. This is B and C. This is C and A. So you can see you'll get all answer correctly. Okay, so 7 minus 4 will be how much? It will be 1 by CC. Correct?
Yes.
So 1 by CC is this much. So CC turns out to be how much? Now you can see CC is C3, CA is 1, and CB, B. That's fine. Now all are perfect. So how to remove the answer? So 4 we can write as CA, we can directly write as summation of all. And in the denominator, what will come? C1. And no need to go back to the formula, you can get it from here. For CB, what is the answer? For
Summation
CB?
CI Cj by C2.
Yeah, so summation CI Cj by C2, and then CC is.
Summation CI Cj by C3.
So I hope this is clear.
Oh, yeah.
Yes.
Okay. So let me show you some of the example that we have solved in past. Can we do it by the delta star? I'll just give you one example. And these are only meant for the when you write the test series of a coaching. They give all such questions which can be solved by delta star only. Some question of Krotov is based on delta star. But JEE questions will not be based on delta star. I mean, it can be solved alternatively, but if you know delta star, you can solve it way faster than other. But the JEE questions are easy enough. I mean, they always try to invoke the basic concept, no advanced concept. So we have solved this question, right?
Yes.
Yeah.
We remove the node like this and we got the answer. Now, if you look carefully, this is also like a delta. There are 3 delta, 1, 2, 3. You can see 3 delta. So if all capacitors are equal, you had solved using the method of symmetry. But what if I change the values? What if I disrupt the symmetry? Then you cannot solve by any of the method except the delta star or the mesh analysis. So I'll choose this 3 point A, B, C. I'll just name it. And I want to replace this by my new star equivalent. So once I'll replace the delta part. So because all are equal values, so what is the summation part? It is 3C square.
Yeah.
And all are C. So this upon any value will be 3C only, right?
Yeah.
Yes.
So in a way, every capacitor which I want to transform will become 3C and 3C and 3C. Correct?
Yeah.
Yes.
Now I can remove this part because this is not required. We have got the equivalent branch. I don't need this also, because we have transformed into and now this looks like a again if you don't want to solve by symmetry, you have to reduce the, because these two we can combine. right? These two can combine because these are in series, and therefore this will become another delta, which you can further reduce without using, or if you want to invoke the symmetry, this branch we can remove, right?
Yes.
So this is exactly on the line of symmetry.
Yeah.
So if I remove this branch, what will happen? We have C, 3C, 3C, C in series, right?
Yes.
So 3C, 3C is 3C by 2, C and C is C by 2, which is 3C by 2 by 4, which is 3C by 8. So the entire term from here to here, this will become 3C by 8, and the 3C by 8 and C by 2 will be in parallel. So the net answer is how much?
7C by 8.
And that was the answer, if you remember.
Yes.
So delta star is a powerful method, but should not be thought much about it, because most of the question you can solve by other symmetry and other relationship which you have learned. Only in a situation when there is no option, we try to invoke delta, and you can repeat the delta star transformation as many times as you wish till you get it right. So it will only increase the calculation complexity, but it will make sure that it will solve. Okay. Now, from the current chapter, we also have something called the Wheatstone bridge. Okay. So problems based on Wheatstone bridge, and you can clearly see the spelling of bridge is wrong. So the Wheatstone is the name of the person. Okay. So what happens in this case if we have a circuit which is called the 5-branch circuit, 5-branch, and if the terminals are perpendicular to the bridge element or the bridge branch, then only we call this as a Wheatstone configuration. So this is the Wheatstone bridge configuration. We have 5-branch circuit, and every branch, let's call C and D, every branch will have some capacitance. And again, this will have very nice concept of symmetry. Imagine, okay, before that, I'll give you something called, or I might have given, I don't remember. So we have something called charge divider rule. Have I given this method, charge divider rule?
Yes.
So this rule is for the parallel circuit, right? So for
Yes.
two parallel branch, for any two parallel branch, if we have two capacitor and if a charge is coming here, we know the potential across A and B must be same via both paths, isn't it?
Yes.
So we know the charge will divide in the proportion to the capacitance.
Yes.
So if the upper branch gets Q1 charge, lower gets Q2 charge. So Q1 by C1, which is the potential across the upper capacitor, and Q2 by C2 must be equal because they are in parallel combination. So what I'm trying to demonstrate here, that the division of charge depends on the ratio, not the exact value. So whether C1 is 1000 and C2 is 500, at the end it is a ratio by 2 only. Okay. So if we have two capacitors in parallel, the division will take place as per the ratio. Okay. Understood?
Yes.
And that is why the sum of the charge we know is Q. And what matter for the division is the ratio decides the division, not the actual value. So we can tell the charge on each capacitor only if we know the division, I mean the ratio. The exact value of capacitance is immaterial. So if I know the C1 C2 is ratio by 1 by 2, the charge will divide into 1 by 2, no matter how much is C1, how much C2, it really doesn't matter. So we can say that, okay, we can, from these two equations, we can calculate the individual charge. So the Q1 will be how much?
C1 upon C1 plus C2Q.
And so the Q2 will be how much?
C2 upon C1 plus C2.
I hope this is clear.
Yes.
Now, when we have a 5-branch circuit, then the middle branch is equidistant from both the ends, right?
Yeah.
Now, when some charge will reach here, and if the C1 and C4 will have the some ratio, let's say C1 is 5 and C4 is 10. What is the ratio? 1 by 2.
Yeah.
Now, if I take this as 2 and this is, if I take as 4, what is the ratio?
1 by 2.
See, if you manage the ratio on both sides, then the symmetry rule says that the charge must divide similar in both directions. So if it will get Q1 and Q2, the same ratio should be arriving here,
Yes.
which seems like the Q1 has totally surpassed the point C and 2 has gone here and the middle has got nothing. Do you realize this? The
Yeah.
middle will get nothing. Which means if the ratios are maintained in a similar fashion, then the bridge element or the bridge branch will not be the participant of the charge or the current in the circuit. Is this clear what I'm saying?
Yes.
Yes.
The rule is they should maintain the ratio. So value becomes immaterial. What really matters is the ratio. So 1 by 2, C1 by C4, if managing the C2 by C3, we can always expect the middle will get nothing. Okay. So that condition, when the ratios are maintained, is called the balanced Wheatstone bridge. So we say in balanced Wheatstone bridge condition, the ratio on each terminal side must be equal. So you can say C1 by C4 must be equal to C2 by C3. But this can be rearranged in multiple ways. So the one way of writing is 1 by 2. You can also check the ratio this way. So 1 by 2 is 4 by 3. And the last way of writing is the cross multiplication. So we can add 1 and 3 is 2 and 4. And this is really the striking way of remembering that if the cross product of capacitance or resistor are equal, which is the same way of saying that the ratios are maintained. And if the ratios are maintained, then the connecting bridge element will not be the participant of the charge or the current, hence can be omitted before reducing the circuit. Okay, are you getting the idea what I'm saying?
Yeah.
So in a way, what is happening here, the balance condition will force the potential of C and D to be equal. Okay, it will force the potential of C and D to be equal, and if the potential is equal, then the flow will not take place, and therefore this branch, although physically present, is electrically not contributing anything, isn't it?
Yeah.
So what we write is, I have written something here. Okay. So in balance condition, no charge oblique current will flow to the bridge branch. Okay, so if you connect some galvanometer, you will see no deflection, no flow will take place. So in balance condition, no charge current will flow through the bridge branch, hence should be omitted before reducing the circuit. I hope this is clear.
Yeah.
So I'll give you a quick circuit. Let's say this is A, this is B, and we have capacitor here, C, 3C, and say 12C, 3C, 9C, 4C, and then we have one more capacitor of value 2022C. Now, if I give such value, it means you're smart enough.
Yes.
I mean, of course, I don't want to use it. That's why I've given. But you can see something. If I come at this end, I can see the ratio of the branches how much? 12 by 9, 4 by 3,
4
and
by 3.
which is exactly same on the other side also.
Yes.
Also, you can see the cross product is same. 12, 3 is 36, 9, 4, 36.
Yeah.
Also, the ratio this way is same. 4, 12, 4 is 3, 9, 3 is 3.
Yes.
In multiple ways, you can see the ratios are maintained. So if you come across such circuit, then the central one, the middle one can be omitted.
Yeah.
So sell it, throw it, and therefore this can be reduced into this circuit will look like only this circuit, which we can all reduce, right? We know the series parallel combination, and therefore you guys are free to answer. So what will be the C equivalent?
21 C by 4.
So 12 4 is 3, right?
3, yes.
9 3 is 9 by 4.
9 by 4.
So 3 and 9 by 4 in parallel. So 3 plus 9, 9 by 4 is how much?
21 C.
I hope this is clear.
Yes.
But it is not necessary that you will be able to see the Wheatstone bridge always. It sometimes comes in disguise. So in a circuit, it will be like camouflaged. I mean, you won't be able to see it very easily. But if you look carefully, you can see it. So I may create a circuit like this. To make it simple, I keep it simple. Now, do you see the delta? I mean, sorry, the Wheatstone bridge, balance one? Okay, tell me, what is the answer for this? What is the CAB? So are you guys able to see the, I mean, the Wheatstone bridge? That tell me the answer. What is the answer? Tell me quickly. So which capacitor we can throw out?
So the left.
Diagonal one, yeah.
Yes.
But if whatever is entering here will have the same ratio. So for if I cut from here, because this is perfectly a separate branch, so this we can solve separately. Understood? Because the interaction of this entire thing is happening in isolation with the rest of the circuit. So we can throw it out, and therefore the rest is simple enough to carry out the calculation. That's why I say it will always come in disguise. What is the answer? Tell me. Come on, guys. What is the answer? C by 2. This is C by 2. C. So this is 1, 2, 3. 1, 2, 3, 4. 4 C by 4. So C by 4 plus C is 5 C by 4.
5. Yes, sir.
Understood?
Yes.
Everyone, tell me, guys.
But
I'm
is
not
it necessary that like the Wheatstone bridge should like be the diagonal or something like that?
No, it should form a five branch circuit.
Okay. Yes.
The branch net value should be in such a way, like the every branch should have net value, and the net value should be measured. So we take the branch value. In one branch, you may have infinite values. Understood? I'll show you one more. Now, if I ask you what is A and B,
So now the middle wedge will be Wheatstone.
now the
Middle wedge.
this entire term, right?
Yes.
So all will be go away because I have given the value such a way that 2C, 5C, 7C, 7 into 4. This is entirely now. If you reduce it,
Yes. Ha.
you may end up looking at or
28,
seeing.
28. Yes.
Yeah. So sometimes you have to reduce to come to know, okay, this is the Wheatstone. Now, what is the trick? The trick is simple. The toughest question of JEE is based on Wheatstone. The moment you see question is very tough, try to look for the Wheatstone. That's it. So now you can see this is 1537 plus 18 is how much? 50. Am I right? So you can see clearly it's the ratio is again same, right?
Yeah.
At one go, you won't be able to see. It is not necessary that at very first go, but what you do is, if you know that you can reduce a part of the branch or circuit, reduce it. Reduce every part which you can possibly do it. And once you have reduced, then try to look for the Wheatstone. You will find one. Okay.
Yes.
Yes.
In fact, for this question, this is also line of symmetry for this particular part of circuit. So I'm not saying for the entire circuit, but this part is quite an isolated circuit because this is the well-defined terminal. And because for this well-defined terminal, we have this line of symmetry. So we could have removed because of the line of symmetry as well. It's the same logic. Okay. So the Wheatstone bridge is more generic than symmetry. Symmetry means both sides is same ratio and same value also. But in Wheatstone bridge, the same value is not required. The same ratio is required. So therefore, I can say the Wheatstone bridge is the stronger form of symmetry situation, isn't it? It is much more stronger. The third variety, which will find really challenging, so when you totally fail to see it. So again, it's a very famous question. One, two. So it looks like the short circuit problem, which we did in the very beginning,
Yes.
but we don't have any short circuit. We have capacitor everywhere.
Ha.
So what is CAB? Are you guys solving it?
Yeah, just a sec.
Receive, tell me the answer. Can you tell me the answer? Archit, have you understood the concept? Hello guys, am I audible?
Yes.
Yes, sir.
Yes, Archit, tell me. If you have understood, can you reduce it? Can you got the answer? Kanu, are you there? Kanu, are you there?
Yes, sir.
Are you solving it?
Yes.
Tell me the answer. Receive, what happened? You have done this before also. So do you see the Wheatstone page here? You can redraw and you can get it. You can number it 1, 2, 3, 4, and 5. And if you look carefully, the 2 and 3 is like a middle branch. And then 1 is for connected to 2. There's 1, 2, and there's 1, 3. So we have direct capacitor from 1 to 2 and 1 to 3 as well, right? And sorry, from 2 to 4, we have one direct, and 3 to 4. And then 4 to 5. So this is equivalent of this circuit. And do you see the Wheatstone now?
Yes.
So we can basically remove the
Middle.
So once you remove it, what you get? 1, 2, 1, 2. C, 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 and you know how to get it. So what's the answer?
Uh, uh, C/2.
C by 2. Very good. So everyone is okay with the
But
C by 2?
I'm not getting it how to strike that Wheatstone will be this.
So today you saw, then next time you have to think about, okay, if something like this will come, you have to strike. This should strike.
Okay.
Of course, no one can imagine about the galaxy until you have seen some pics of it. So every thought, comes when we have some experience of the past. Now, these are the experience which you need to create the next level experience. Okay, so everything you need to know, you have to see, and then you have to develop the intuition later on. If you're really lucky, you can develop at very first go without any support. So in the beginning also, I struggle a lot to understand circuit, but with practice only, I would say that eventually I realized that, okay, these are the things that I need to look for, and then from that day onward, I started, figuring it out, like what kind of symmetry is possible, what I can see possibly. So it is a tough task. I mean, I won't say it's very easy. So I hope this is clear.
Yeah.
C by 2, C by 2, C's, and C by 2. So the answer is C by 2. Okay. So one last problem based on the Wheatstone. So do you see this is Wheatstone? Do you see this? You can see it. If you make some sort of flip flop, you can see it. So not able to see. Just
Sir,
flip.
able to see. Got it.
Just flip this side.
Yeah.
You have to play with the circuit. You have to just flip it, and you will see that it's the same circuit I have redrawn into this shape. So both are same circuit, isn't it? You just take this part inside here.
Yeah.
And this part inside here. You will see the same circuit, isn't it? All short of manipulation you have to think about. I mean, there is no way or there's no book written which can teach you all this thing. So some manipulation we have to figure it out on our own. And therefore, the more you see, the more you will get the better picture of it. And the more you attempt. Is this clear?
Yes, sir, got the answer.
So this is same as both are same.
Got it.
So the C equivalent is
See,
C. The last variety that you can create. I mean, of course, the infinite question you can create, but we have to stop somewhere. So this is the unique question. At first go, it will not look like a Wheatstone bridge for sure, but it is. So let's say this is C, this is C by 2, C by 4, C by 8. And this is if I call a better value. Yeah. And same here. And then what we have is so it will not look like it is a Wheatstone bridge, but if you look carefully, the ratio is maintained as you progress
So the
forward.
ratio is
Yeah.
yes.
So C, then 2C, then 3C,
Yes.
3C. And therefore, all of the middle branch we can throw out.
Yes, it will.
So we can throw out all of these. And therefore, the CAB will be simply a bit complex because it's 1 by 1, 2, 3, 4. How much is that? 12.
Yes.
18 plus 4, 22, 25.
25.
So the
24 by 20.
it's 24 by 25, right?
Yes.
So with this, I will end the circuit types of circuit which you will come across. There are a few more types that we'll discuss in a different context, but not now. So we are going to start something called rules to solve circuits. So there are many rules that we need to understand. I mean, which is employed to solve circuit. At JEE level, there are very few. At BTech level, there are still very few. And same logic you have to apply there also to solve. Okay. So I'll show you every method that one should know or be aware of to solve most of the circuit mentally. Okay. So most of the JEE question you can just solve like this. So I'll just reiterate the charge divider rule which we have done. So quickly I will just finish drawing it. So we have done this before. So if you know what charge is coming here, and if you know that we have capacitor here, so the charge which will divide here will be in the ratio of what? Capacitance.
C1 by C2. Yeah.
So when it comes to the calculation of charge, so we can say Q1 equals to, okay, so Q1 by C1 equals to Q2 by C2 because the parallel concept. And this implied again Q1 by Q2 is C1 by C2. And we also know the sum is Q, so we can write as Q1 equals to 1 by 1 plus 2 into Q, and 2 equals to C2 by 1 plus 2. Okay, so we have done this. I mean, that's for it's meaningless. Now imagine a circuit. Let's say the application of this idea. So we have something called, I'll just put a name for your memory. Actually, this is like a memory aid. So in circuit, you will come across two types of question. One, which is called the reducible circuit, in which the given circuit of capacitor, you can find the equivalent capacitance. So if it is feasible to find the equivalent by hook and crook, we call it a reducible circuit. When I say hook and crook, it means either by the basic symmetry and other arguments, or the delta star in worst case scenario. So if we really have the reducible circuit, then we employ this technique. So to solve questions which are purely reducible, so let's say so you can clearly see something here, that all of the capacitors are jumbled at one place, right? And battery is totally separate, right? So battery or the energy source is not getting interfering with the circuit. It is like you have just two terminals which you connect across. So what I have encircled, the bigger one, can we reduce it?
Yes.
And if we can reduce it, what is the C equivalent? Tell me. Everyone, tell me the answer.
11C by
By
5.
5. I think that's correct answer. So anybody else getting the answer? 3C, 2C are in series, which is 6C
Yes.
by 5
6C by 5.
plus C, which is 11C by 5. That's pretty simple answer. Now, how to approach is we always start with the charge coming from the cell And because we can reduce into a single capacitor with single cell, the total charge we can calculate at first go. So we always begin with writing the net charge, and we write as C equivalent into V. Is this clear? So the total charge value here is how much? 11 CV/5.
Yes.
Are you guys clear till far so far?
Yes.
Okay. So what we do is we move along the charge. So let's walk. Everyone, let's walk. So if I walk along the charge, I'll come till this point as a Q. But at this point, I am having a dilemma, because now I see two branches. So I need to know that the total C of the upper branch, because this part is in parallel with this part. Do you realize this?
Yes.
So what is the net value of the upper part
6 C/5.
and the lower is
C.
C? So is it the ratio is 6/5?
Yes.
The ratio is 6/5, 6 for the top and 5 for the bottom,
Yes.
isn't it?
Yes.
So how much charge will enter in the upper branch? Can you guess?
6 Q/. Yes.
And the lower?
5 Q/11.
Very simple. Understood.
Yes.
So you can clearly see the charge distribution. Now, once you move further with the 6Q/11, you reach another junction,
Yes.
and again you see the division. But now the division is simple.
1/2.
So it will get 1/3.
Yes.
So 1/3 of the coming is how much? 2Q/11 and 4Q/11, isn't it?
Yes.
But these two will again meet here. So again we have 6Q/11 here.
Yes.
And now you can see, you know exactly charge on each capacitor. So what is the charge here? 6Q/11 here, 4Q/11 here, 2Q/11 here, 5Q/11, and you know Q also at the separately. You know Q answer.
Yeah.
So if you want to find the net charge, you can just multiply with the Q value and you're done. Understood? No? Yes. The other way of thinking is this. Because we have parallel branch, so the voltage across each parallel branch is V only.
Yeah.
So this will be exactly equal to CV. If you substitute Q, you will also get CV. Because the potential across the lower branch is V, capacitance is C, the net charge must be CV, isn't it?
Yeah.
And the net charge, net capacitance of upper branch is 6Q/5.
Mm.
Sorry, 6C/5. And the potential across is how much? V only.
V.
So 6Q/5 into V is 6C/5 into V is 6CV/5. So this answer itself is 6CV/5, isn't it?
Yes.
If you have multiple parallel branches, you can treat each branch with one battery and solve it separately. No need to do the overall division. Is this clear?
Yes.
And once you know charge of each capacitor, you can easily find the potential of each capacitor. By which formula? Q/C.
Q/C.
So charge on the given plate upon capacitance will give you the voltage across that capacitor. So a lot variety of question you can solve only if you know the basic charge divider rule. Is this clear?
Yes.
Let's do some more practice, everyone, and you all have to tell me the answer. A very simple, typical circuit. See, it's so simple, I can add all values. Can you find charge for each plate? Okay, let me make it slightly easy. See, you see. Yeah, tell me the answer. Can you find charge for each plate? You can do almost 20. So first of all, is it a reducible circuit? Yes or no? Is it reducible?
Yes.
Yeah.
So if it is reducible, then can you find the C equivalent?
Yeah.
What is C equivalent?
Pi C by 6.
Very good. So how much charge will leave the battery?
Pi CV by 6.
Correct.
Yes.
Now that total charge will appear here.
Yes.
So the first capacitor will get entire charge 5C by 6.
Yes.
But the same charge will reach here and will get a junction.
Yes.
But we know that whenever you get a junction, you can see there are parallel branches. These are parallel.
Yeah. Change.
So the charge will divide as per the charge divider rule. Which ratio? C ratio.
Yeah.
So this will get how much? The 2C will get how much?
CV by 3.
It will get 2/5 of
Yes.
which is CV by 3.
And the 3 will get CV by 2.
We know every charge, isn't it? And all of these we are doing
Yes.
mentally. There is no need to solve much. You can all do mentally. And because you know the charge on each plate, you can also find the capacitance voltage. So what
Yes.
is the voltage across this one? Q by C. So voltage across 2C is how much? V by 6. Do you realize this? Yes or no? And voltage across this is how much? Tell me. Come on.
By
It is parallel, so it must be same, no?
Same parallel. Yes.
Whether you write Q by C, so first you find the charge, then you can find the Q by C formula to find the voltage across each capacitor,
Yes. And that will be 5 by 6.
and the rest will be 5 over 6. Correct. Are you guys able to realize this?
Yes.
Yes or no? I'm not listening to everyone. Tell me, everyone.
Yes.
Atharv,
Yes.
Garb,
Yes, sir.
Rishiv, Kanu,
Yes,
Mudda.
sir.
Okay.
Yes.
Are you all able to understand this part? Okay. So once you get this, of course, see, I am using one of the method to get this answer. The same question can be solved 1,000 ways. Okay. So most of the JEE problems are based on this simple idea. And the more you know, the more you can play with circuit. And the next is called voltage divider rule. So we apply this rule for only two capacitor in series combination. Imagine we have a battery. So the total potential difference across both capacitor will be equal to V, isn't it?
Yes.
But the potential across each will be a part of V only,
Yes, sir.
not V. And because they are in series, can we say the charge must be same? Whatever the charge, it must be same.
Yeah.
So we are not going to calculate charge, but we can say the Q must be same, isn't it?
Yes, sir.
So the ratio of voltage will be by definition Q by C1 by Q by
C2
C2.
by C1.
So what you can realize, it's an inverse ratio, isn't it? And it's a logical. Why? Imagine the same example, the bucket example. The same charge is like same water.
Yeah.
And C1, C2 like a base area.
Hmm.
Yes.
So more the base, lesser the height,
Right. Yeah.
Yes.
because the amount of water is same.
Yes.
Yes.
So voltage will be in the inverse ratio of base area, or you can say capacitance. Is this clear?
Yes, sir.
So no need to solve because we know the total voltage is V. So I can directly find V1. V1 is how much? C2 by C1 plus C2 into V, isn't it? The inverse ratio.
Yes.
Yes.
And therefore the V2 will be 1 by 1 plus 2.
Yeah.
Okay. So let's go back to this question again and try to solve this question with. So anytime I can redraw the circuit. So I can redraw the circuit as do you realize this? It's the same circuit.
Yeah.
And 2C and 3C we can reduce, right?
Yes.
Because
Five.
then probably 5C. So
Five.
basically, if you look carefully, there are only two capacitors in series,
in
5C and C and 5C, right?
Yes.
So voltage will divide in the inverse ratio.
Yes.
So the 5C will get 1/6.
Yeah.
And that
C
will
will
get
get 5/6.
5/6.
5/6.
See, we are done mentally. You can see
yes.
answer. And because I know the potential difference, I can write the charges, the difference into charge. So 1/6 of 2C is,
C/3.
so V by 6 into 2C is CV by 3. So you got
Yeah.
the charge also.
Yes.
Are we able to do it mentally? Yes or no?
Yes. So we can solve it in either way, right?
Anyway, I mean, see, this is only two methods. We can solve in at least 5 to 6 methods.
Yes.
So very soon we are going to solve using a third method. But see the power of methods. I mean, every method will have some privileges. So can you answer the question without using pen? Okay, I'll give you a question. Tell me the answer. Don't use any pen. Just do the mental calculation. The values will be simple. Don't worry. So I'll make it more realistic as the books will give you. And that's why I say always the real value doesn't matter. What really matters is the ratio. Can you find the voltage across each capacitor without solving?
Yes.
What is the answer?
First 2 on 2 it will be 9
Yeah,
and then 3.
3. I mean, there is no option. 9 and 3.
Yes.
So it is a ratio is 1:3. So 3/4 and 1/4.
Yes.
So 3/4 of 12 is 9. Done.
Yeah.
And so you can find the charge on each easily, right?
Yes.
Yes.
Charge is Q equals to CV. So charge on each plate will be how much? The upper plate will be
18 and 18.
18
18
micro,
is-
yeah, 18 microcoulomb. And so if I say Q1, this is okay, but what are these are in
They will be
series?
same because
Yeah, so here see, so you can say anyway, it's 18 microcoulomb. No matter which one you use, you are going to get the same answer, right?
yes.
So all done. It's very simple. Can you find the charge on each plate mentally?
Yes.
Tell me the topmost, the 1 microfarad. Quickly, what is the potential? Okay, what is the potential? See, it is multiple branches in parallel. Do you realize this with battery?
Yeah.
You can mentally treat each branch, each horizontal line as one branch and solve mentally. Okay? Not okay.
Okay, sir. Yeah.
Tell me the answer. Yes, Kanu, are you getting it? Kanu, if I listening to me, reply. Is this clear?
Yes.
Tell me the answer. Okay, everyone be ready with the answer. I'll ask question, you will answer it. I'll ask randomly anyone. So once you're done, tell me. Find all voltage, all charge, and be ready with the answer. Everyone. Okay, I hope it's done. So tell me, who will tell? I'll ask anyone. Yusuf, tell me the charge on 6 microcoulomb, 6 microfarad capacitor.
Charge.
The charge.
So, sir, the calculation is a bit tricky.
Why it is tricky? It is mentally. You can do it mentally, and there is no need to use anything. The 18 volt is across which two branch? 6 and 4,
Yeah,
and these are in series, right?
yeah,
So this voltage will divide into series combination in a inverse ratio.
in inverse ratio, yes.
So 6 will get 4 by 6, the 4 by 10.
4 by 10, yes.
So 4 by 10 into 18, how much?
Yeah,
Is it
okay.
tricky question?
No, no, no.
Then
I was completely solving.
so why assume completely? That's why circuit is difficult for all. We all try to solve something different. In circuit, you need to realize that this battery is a potential giver, and it is connected here and here, which means every branch across this will have same potential. So it is as good as you can break into a circuit of with each branch and each. Until you will not break the circuit, you won't be able to solve it with ease. So these kind of calculation we do it mentally most of the scenario. All the JEE advanced questions are mentally solvable questions. They don't have any worth. Okay, like this. So now is it easy now? So what is the charge in the 1 microfarad?
That's which
1 microfarad, how much is
3,
voltage?
3,
How much is voltage?
12 volt.
12.
Hello.
Yes.
Yeah,
It's 12
12.
volt. If the voltage is 12, the charge will be 12 microcoulomb.
Yeah,
Okay. If it is micro, it's microcoulomb. If it is farad, then coulomb, right? You can
coulomb.
say like
Yeah.
this. So who will tell me the charge on the 2 microfarad in parallel one? Mugda, tell me. The charge on the 2 microfarad in the
Like
parallel
the
one.
down one.
The down one, yeah.
One.
How much is it? What is the voltage by the way? Voltage is how much across every capacitor in the 2 microfarad in parallel one, the middle one. What is the voltage across this? Tell me guys, voltage. Tell me everyone. Anyone, what is the voltage? Come on. What was the ratio of voltage?
6 by 10.
It is 6 by 10. So 6 by 10
Into
into 18, na?
Yeah,
So 6 by 10 into 18. 18 6
54 by 5.
54 by 5. Final.
54 by 5. Okay. So what is 6 into 18? 6 into
108.
18.
108.
So by 10 is 10.8.
10.8.
Yes.
Yeah.
So 10.8 is the voltage. So what is the charge on each? Into 1.6
Into
microcoulomb.
1.6. Yeah.
Yes.
Aren't we able to do mentally? I mean, if I'm not able to do mentally, there is no way of. It's a wastage of learning circuit. So what is the charge on this capacitor? Who will tell? Tanishi can tell. Tell me. Charge here is how much? I think she's there. So what is the charge there? Tell me.
Sir, is it 12?
It is 12. 1/3 of 18.
1/3 of 18 will be 6.
12.
and then
That's
No,
okay.
6.
Yeah, so that's correct. So the
12,
charge is 12 microcoulomb.
yes.
Correct. Is this clear to everyone? Yes or no?
Yes.
All right. So let's do some more practice. Okay, find the charge on each capacitor. Just a minute. Just make it 1/5. This is fine. Just a minute.
Yes.
Yeah, this is fine. This is easy to solve, right? So tell me the charge and potential on each capacitor.
Hello.
Yeah.
Sir, I think I got it.
So we'll start with this one.
First, I found C equivalent.
Yeah. So what is C equivalent?
1.
Mhm.
Yeah, C equivalent is 1.
So 2/3.
So 2/3.
2/3, right?
Oh, no, sorry. I told only of that part. Okay.
Okay, this part is 1 you're saying,
Yes,
right?
yes. Okay.
Okay, that's fine. That's fine.
Okay.
So that's correct. And then, yeah, you can find the net charge, right?
Yeah, that will be 4
Yes,
microcoulombs.
2 by
4 max.
4.
Net is how much?
2 by 3 to 6.
4
2/3 into
4
microcoulomb.
6.
microcoulomb.
Yes.
And now you will work the circuit. You know how to work.
Yes.
So this will get entire value, right? Full value.
That will get 4.
Yeah.
But it will come here and then there's a division.
Yes.
What is the ratio of division? 4:1?
4 by 5
4
and
is to
1 by
yeah.
4/5, and yeah, correct.
1 by.
So this will get 4 Q by 5, right?
Yes.
Yes.
And this is Q by 5.
Yes.
We are done. And because we know charge on each plate, we can find potential that's okay.
Yes.
So I think some more practice. Huh? Was it enough? Can we go to next concept? Or you want more practice? Just let me know.
I got
I got it.
I hope you all are okay with this. Like you know how to proceed and how to solve.
Yes.
Yes.
Yeah.
Okay, so I'll go to the next concept. So we're done with the basic, very basic way of solving question. And that's why circuit is not something difficult. You need to understand that how potential and how we can break the circuit into a small segment, and we can treat each segment separately and solve it and then recombine to make it okay. Okay, so the next is called circuit laws. So we have two circuit laws. The first is called Kirchhoff's current law, also called Kirchhoff's first law, and we can also call it KCL. With a lot of love and affection, we call it KCL. So this is given in the honor of Gustav Kirchhoff, and you may be wondering why these laws are given. So these people are not solving question of a circuit; they were solving the question of either superposition or conservation. And because whenever there is a law of conservation or law of superposition, these laws come naturally and automatically. Okay. So in computer science also you will study a lot of circuit. So we call the graph circuit or the graph theory. So like the Facebook uses the graph theory to understand the connection, like how many friends you have in your connection. So you have your friends and then your friend will have some friends and they will have some friend. So you can reach any friend by traversing the friend of friend in most of the cases. That's called the reach. Okay. We use the Kirchhoff's law to decongest the traffic in a city. Okay, so all things where we have some flow associated. So let's say we have the conservation of vehicles on a road, and we have multiple diversions or the routes. So we want to, kind of spread the traffic into multiple pathways to reduce the congestion. Okay, so all this uses the concept of Kirchhoff's law. Okay, so we'll see how things are there actually. So Kirchhoff current law talks about something called the steady flow of current. Okay. So this law is consequence of conservation of charge and it is applicable in a circuit only when no part of circuit participate in accumulation of charge such state of circuit we call steady state or equilibrium state. So according to KCL, at any junction in the state of equilibrium, total sum of incoming charge must be equals to total sum of outgoing charge or the total algebraic sum of charges or charge at any junction is 0. So when you invoke the second definition, we invoke the sign convention, which means we take incoming as positive, then we have to take outgoing as negative, or vice versa. If I employ the first definition, I just write the values. The incoming value equals to outgoing value. And if I choose everything as incoming, we have to put outgoing as 0. If I choose everything to be outgoing, we have to equate the incoming to 0. Okay.
Yes.
So a large variety of circuit can be solved simply using the Kirchhoff's law. So let's say I'm representing a junction connected with a large number of capacitor. I'm just showing you 3. The remaining part of circuit is not shown. What else you know? The potential of the terminal, or you can say one of the terminal of the capacitor. So let's say this end is maintained at potential V1. How it is known, that is a different question. But as of now, we have to believe that this end is at potential V1. So V1 is representing potential. The way we have learned in electrostatic, the potential, not the potential difference. So V1 is not the voltage. What is V1? Only the potential. So
Potential.
similarly, this is, let's call V2, let's say call V3. So if we assume that V1, V2, V3 are given or known to us, if V1 and V3 are either given or known, then to find the either charge or voltage across every capacitor, we just need one more variable, isn't it? And which variable we need? The potential of junction, because the moment I know V, I know the potential difference of each capacitor, isn't it?
Yeah.
Because other end is known to us, but one of the common end is unknown to us, which is called junction potential. So if somehow we can calculate the junction potential, can we find the charge on each capacitor? Yes or no?
Yes.
So can you find the potential difference each capacitor? Definitely yes.
Yes.
So how to proceed and solve question like this? Okay.
That we need to find this potential of the junction, right?
Yeah, potential,
Not the,
not the
voltage.
difference. Difference we will calculate later on using these two,
Yes.
these two, and these two values. Understood?
Yes.
And after calculating the difference, we can find the charge also. Q equals to CV. Because in the formula of Q equals to CV, the V represents the difference, isn't it?
Yes.
V represents the. So when I write Q equals to CV, the V is the
Different.
potential difference.
Yes.
PD across C. But here V1, V2, V3 are representing what? Only potential.
Potential.
Is this clear?
Yes.
So to solve such question, we will use the Kirchhoff's current law, which says that for any junction, let's say if I have any junction, and if I represent some charge to be arriving, at any junction, if I invoke the first definition, I will write the summation of incoming is outgoing, and we can add and write both the terms separately. So what is incoming here? At this
Q2
junction,
plus
1 plus 2 plus,
5.
and what is outgoing?
3 and 4.
So because the way we assume, we can write the equation, that's it, isn't it?
Yes.
Now, when we solve question, the charge flow direction is not known to us, and therefore, the first step is we have to assume something. So how to assume? It is the choice is with us. So let's say all are coming towards the junction, because that is the easiest way. Or you can assume all are outgoing, or you can choose some of them as incoming, some of them as outgoing. But no matter what is your selection or your choice, mathematically all will boil down to the same thing. So mathematically it won't be difficult.
Yes.
Understood?
Yes.
So what you can write here is mathematically. So I am choosing everything is going, let's say Q1. And the way we choose the flow direction also tell us about the high and low potential. So by choosing V, I mean every charge to be away from the V, can we say V is the highest potential?
Yes.
And once we decide that V is as highest potential, writing the potential difference is not a big deal. So using KCL at junction, can we write a Q1 plus Q3 equals to 0? Because we don't have any incoming, right? And now we are going to invoke this relation, Q equals to CV. So what is Q1 representing? The charge which has flown across C1, which means the charge which is stored on the first capacitor. That is also way of thinking. Okay. So tell me guys, what should I write here?
C1
Uh,
into V minus V1.
Very good. So do you guys agree with what Christoph said?
Yes.
Yes.
So similarly, what I should write Q2,
P2 into V minus V2.
and similarly Q3
V
as
minus V3. C3 into V1.
C3, yeah, equal to
And I hope this is not very difficult to solve for V.
no.
Yes.
So V turns out to be the C1 V1. Although I have done it for 3, you can extend for any number. So in general, this is true for 2 to any number, not just, you can do it for any number. But the problem is we need potential. We don't need potential difference to apply this method. I need to know the potential, isn't it?
Yes.
And this is really the biggest weapon in solving circuit. Most of the challenging problem we can solve using this simple trick. Okay.
Yeah.
So based on this idea, we are going to solve some of the question today only. So rest of the time today we are going to dedicate for the KCL only. And based on KCL, we have a way to solve circuit called nodal analysis. And you have to learn this. You have to learn this at any cost. If you want to master circuit, this is the secret. So what exactly we do in the nodal analysis? I'll begin with the same question that we have solved before. Okay. So let's begin with the circuit, and this circuit is, I would say, in a form which is very suitable for this kind of analysis called nodal analysis. So in this analysis, what we do, first of all, we look for the battery, and once I remove the battery, the remaining circuit should look reducible. So if I remove the battery, do you see the rest of the circuit as reducible?
Yes.
I hope
Yes,
so. You
sir.
can see.
Yeah.
So in the nodal analysis, the first step is remove cell. So once you remove it, how it look like? Okay, this is our circuit, right? So we have removed the battery. What is the potential of voltage of the battery? It's V. So because the KCL is only applicable if we know the potential. So what we do is, as a trick, we remove the battery, but the end that we create out of this removal, we assign some potential which can match the net difference. And therefore, it is generally convenient to choose one as V, because that is high potential, and other is 0. Now, on the right circuit, the V and 0 represents potential, not potential difference. And it is still maintaining the net difference as per the original circuit. Do you realize this?
Means on the right side, the V is potential.
Yeah, of course.
Yes, got it.
You can achieve in many ways. You can say this is V by 2 and this is minus V by 2. You can say this is 2V and this is V. You can choose any value of potential which can keep the difference as same as the original circuit. That is the whole idea. But choosing 0 is really convenient, isn't it?
Yes.
So we generally choose 0 for one and V for other. If you want to choose something else, you are free to choose. But I'll recommend use 0 and V. Any doubt so far?
No.
No, sir.
Now look for the equipotential points if you can see something. So I can see 0 is here. This is also 0.
Yeah. All three are 0.
All three are same. Okay. Can you look out for the junction? Once you have done this, can you see the junction? Just okay. So the next step is look for junction. Apart from terminal. And I said a junction is the place where at least more than three connections are present, right?
Yes.
So I can see this one, I can see this one, but this is already known to us, the value. So I'll look for the unknown one. So which junction having unknown potential? Do you see this answer?
Yeah.
So how many of you are able to see the unknown junction?
Yes.
Everyone?
Yes, sir.
Yeah.
The next step is choose some value. I'll always choose X and Y because we are good with solving equations in X and Y. So let's call it X. Okay.
Yes.
Yes, sir.
And now we are in a position to invoke the KCL. Why? Because except X, every other end, every capacitor which is connected at X, those capacitors other end potential is well known to us. Do you see that?
Yeah.
So from X, how many capacitors we have? 3 capacitors. C1, C2, C3.
Yes, sir.
And the other end potential is known to you, V00.
Yes, sir.
Yes.
So let me go back to the problem which we solved in the very beginning. Where we solved? Yeah, sorry, here. This one, no? Yeah. So we have taken C2, C3, C. Okay, I'll go let's call this is C, 2C, 3C. Okay. And assign a variable. So okay, we have done till here. What is, can you find using KCL? Either use that formula which we have derived, or you again derive it here. It's up to you. So I will use the answer directly. So using KCL, find X. Find unknown potential. So can you guys write X equals to what? What is X here? We know the answer.
Yes, sir. C times
CV. C times V, 2C times 0 and 3C times 0.
3C. Yeah.
All over, so upon 1 plus 2 plus which is 6C.
6C.
But
And
V
C
by
I
C.
got the answer. Pardon?
what?
And see, so fast. We can do it mentally again. This also. I know the answer is V by 6. And other is 0. So the difference is V by 6 over. And what is the difference between the first capacitor? V minus V by 6.
5 by 6.
And not only that, we can clearly see which one is high, which one is low, so I can assign the proper charge. And because now I know everything, because I know the difference, so I know everything. I know potential difference, I know the charge value. In fact, we can calculate now. So this is such a simple way, right? We're done.
Yes.
And it really doesn't matter which potential we choose because the difference matters. So the choice or the selection is totally immaterial. So if someone will ask you what is the charge on the C2 capacitor, so it is V by 6 into 2C,
Yes.
which is CV by 3.
CV by 3.
Same for the other C3 will be CV by 2.
CV by 2.
And for C it is 5V by 6 into C, 5CV by 6.
Yes.
We are all done, all set.
Yeah.
Do you realize this?
Yes.
Yes, sir.
So imagine if we have a circuit like this. Okay. So we have given this circuit. And let's say they are asking find the charge on each capacitor. Can you do it in one line?
That is even.
Yeah, E1, E2, E3. How to think of Kirchhoff's current law here? And that will solve this question in one line. So let's say I want to know the charge on each capacitor. So for that, what I need to know?
First, we need to remove the battery, right?
Yeah. So first of all, we need to assume some zero, assume some potential, because without potential, we cannot solve.
Yeah.
So I will take the lower end of the battery as 0. The benefit is, if this is 0 and if you cross this point, what is the potential here? If you go from here to here, 0 plus E1 is here.
Yes.
This is plus E1. So this is plus E2. And this is plus E3. So we are able to get the potential of one of the end of the capacitor, isn't it?
Yes.
And you are missing only the other end, which is common. Correct? See, you know the answer for one of the end. And what you are missing?
Other end.
Other
Other
end.
end. So can we get the other end now?
Yeah.
Because this is the direct formula, no? What is V equals to? Tell me, guys. What is the V equals to?
C1 E1
C1 E1
plus C2 E2 plus
C2
C3
plus
E3 upon C1.
yeah.
So now we know the potential. So what they are asking in the, this is the SC Verma question. If you open the SC Verma, you have SC Verma, everyone?
Yeah.
They're asking what is the potential difference between A and B? Because I have taken A as 0, B as V, so the answer,
So
this is
V
the
will
answer.
be the answer.
And you can check, that is a question from SC Verma. You can answer this also. Open the book SC Verma, everyone. Capacitor, go to Capacitor chapter. Do you see something like this problem? This is on the third page, left bottom. Can you see something like this? Third page, left bottom.
Yes, sir. Yeah. Got it. Question 30.
Question 30, whatever. How many of you are able to see it?
Yes, sir. Right.
Yes, sir. Got it.
Can you read the question first? What they're asking?
Mm.
Read? Question is simple.
Yeah.
Find the potential difference between A and B, right?
Yes.
Isn't it?
Hmm.
And we got the answer, isn't it?
Sir, a battery is connected. Yeah. So V is given as 60 and
So
okay.
apply the formula, tell me the answer.
Yeah.
What should be the answer there? Tell me, guys, what the answer?
Sir, 20.
It is 12 volt, right?
12 volt.
No, whatever. I mean, then what is the value?
Sir, I'm getting 20.
20. Check the answer.
Yeah. Yes, sir. 20 volt.
Very good. How difficult is this?
Exercise 30. Yeah.
Okay.
Yeah.
You can see there cluster problem in the same page, in the same section. We have multiple questions, and all you can solve with the same logic. So you can see we have questions. I need to open the book. Just all right. So now probably any question you can see, you can solve mentally. Okay, I'll give you some more trick. So come to, yeah, that's very easy. Question number 25D. Can you see this? 25D.
Yeah.
Can you answer this?
Yeah.
25D. Can you answer this?
Yeah.
Can we answer this mentally? Tell me, guys.
Just a second.
Sir, I'm getting 4.
You're getting
4.
4.
No, 6. No.
6. First, read the heading of the question 25.
Oh. Yeah, sir, I got
How much?
Sir, is it 12?
Is it? I mean, this is formula in front of you. You have formula. Still, you are making the mistake. Huh? 25D. What is the answer?
So 72/7.
Correct. Just it is 24, 24, 24, 72/7.
Yeah, sir, I took that 6. I thought 3 to 1 and not 4 to 1.
Very good.
That why I gave 12. Sorry.
Okay. So VA minus, but they are asking VA minus VB, which means
Minus.
minus. So answer
Yeah.
is minus 72/7,
Minus.
which is roughly 10 minus 10.3, right?
Yeah. 10
You
point.
realize this. Now look at the question 25C. 25C. And if you look at the 25C, you can see something interesting, that the moment you take A at 0 potential, you can find the potential of each point. And see, they haven't given the value also of the middle capacitor, right?
Yeah.
Because probably this is not required. If I say this is 0 volt, this is how much? 2
2
volt.
volts
This is
-2.
this is we can call X. So we can write X equals to how much? -4 plus 4, 0, which is 0.
0.
Answer.
Anyway, this is at 0 potential. It means the middle one will be of no use, no charge, nothing will go there. You can throw it out.
Yeah.
So what is the answer? What is the VAB?
0.
0.
See, all are mentally solvable, right? No need to do any effort. Okay. Can you solve the question number 25? The same way we have done this, right? 25
25 which?
A. Think about how to replace the battery, how to choose the potential. So apply some brain, put some effort, get the answer. Tell me everyone, what is the answer? So we have done this by different method, and now you are supposed to solve by the KCL. How you are going to solve, that's I don't know, but you can solve. Done. Follow the steps carefully, guys.
Yes, sir. 1 minute.
So you have to apply only once. Once you're able to apply, you will be able to apply again further. Okay. It's a one effort. And after today's lecture, you will be able to solve up to question number 60. 61, 62, 63, 64.
Sir, I am getting 12 by 11.
Check the answer. You whatever you're getting, the answer is there.
Yeah, sir, it is right.
Very good. But you are supposed to solve by the Kirchhoff's KCL, the nodal analysis method.
Yeah, sir, I did that only.
Very good. So here the junction potential you have to take where three capacitors are meeting. Which point?
Meeting, yeah.
Which is the 2, 2, and 4, right?
Between.
Yeah, between
Yeah,
them.
between 2, 2, and 4. So what is the potential of that coming? The X is how much coming? The rightmost 2 and 4 are in series, so you can reduce into 1.
Yeah.
Isn't it? So in a branch, if everything is in series, we can convert into 1, right? Okay. Or you can assume some charge as Q because they are in series, so same charge will go to the plate. So it's good to reduce into 1. So 2 and 4 is how much? 4 by 3.
Yes. 4 by 3.
And if you choose one of the end as 12 volt, other will be 0.
Yeah.
So can you find X now? 12 into 2, 24 plus 0 plus 0 is 24 only. 24 upon 2 plus
2
4
plus 4
plus
by 3.
2 plus 4 plus 4 by 3.
Ah, yes. Correct.
So the X we can do how much? How much we said? 12 into 2.
12 into 2 upon 6 plus 4 by 3.
6 plus 4 by 3. How much is that? 22 by 3. 6, 3, 18, 22. How much is this? 11. So it's 36 by.
36 by
11.
11.
Okay. So this is the potential, right?
Yeah,
Yes.
it takes.
So what they're asking by the way? A and B, right?
In.
Yes.
So You can further use the voltage divider rule also mentally to solve, because they are in series combination. Because this is the x minus 0 is the potential across 2 and 4. So VAB is how much? As per the voltage divider rule, we can write 2 by 4, 2 by 6.
Yes.
2 by 6 is how much? 1/3.
1/3.
1/3.
So 12 by 11.
Yeah.
So we got the answer.
Got
We have applied the many rules that we learned so far. We also applied the voltage divider rule. If you know the voltage across any two capacitors in series, you can always divide mentally without solving much. So if you remember every method which you learned today, your journey to master circuit will be really easy. And the idea which we have discussed here, the same idea we have to solve in current chapter. So those questions which require similar idea, that you will solve on your own. Of course, after I'll start the current chapter. But the nodal analysis, the method will remain same. Only the formula that we substitute will be different. So we'll see there also what we have to substitute there and how to solve. Okay. Now, the good thing is whenever we get something like the capacitor and battery in series combination, you can replace the combination by single value, isn't
For
it?
series.
For series.
Okay.
So, you know, this entire circuit, let me give you something more difficult. E1, C1, E2, C2, E3, C3. And let's say then I connect something here. So this theorem, I mean, when you will study the current chapter, this theorem is called the Millman's theorem. But for the Millman's theorem to be true, we must have C1, C2, C3. Some battery may be missing, that is okay. Why? Because if a battery is missing, we can assume as a 0-volt battery. Understood? So imagine you're supposed to find the charge on C. No need to solve everything. You can replace this entire construction by single answer. Because this kind of situation, when we have the E and C in parallel, so for parallel combination of E and C, this you can reduce as a single E equivalent cell, and this single E equivalent cell will be, you know how much? It will be C1 E1, C1 E1 plus C2 E2 plus C3 E3 upon C1 plus C2 plus C3. And all this capacitor we can replace by C equivalent, because they are in parallel, so you just add them without worrying about the battery. And therefore this circuit we can redraw as C, a single cell with the same polarity and a single capacitor. This is E equivalent and this is C equivalent. Okay. And now this is easy to solve because again we can use the voltage divider rule, right? So what is the potential across this? The opposite value, right? So this V we can write as anyone?
C equivalent by C1 plus C plus equivalent into E equivalent.
Yes.
Imagine we have solved a very challenging problem in one line, and therefore the charge on the C is C into V. That's it. We are done.
Yes.
Understood? Yes or no?
Yes.
But this we can also solve taking the fourth capacitor, because the fourth is also in parallel with the remaining three, right? So across these, if I take this as terminal, the fourth is also across A and B, isn't it?
Yes.
But there is no cell, so we can assume,
0.
and I can add the directly answer. So the V I can directly write because V is the potential difference, and the difference we write as C1 E1 C2 E2 C3 E3 C0 upon C1 plus C2. That's it. See the same answer. Is this clear how we have done this question?
Yeah.
So if you have complex circuit in which we have a lot of cell and the capacitor in series, you can replace this as a combination and then solve the remaining circuit. Understood?
Got it.
So we have to actually do one last concept. Do you have time or do you have lecture? Anyone? Kanu, you have lecture? Oh, Kanu is gone. Okay. Krisi, you have lecture?
No, sir. No.
So now this is really important. This is called question. This is very, very important to solve the tougher question of AC or no. Question based on inverse symmetry. So we have heard about symmetry. What is inverse symmetry? Tell me. What is inverse symmetry? Any guess? So I will take a simple diagram. The circuit we have seen before. And if I say this is C and this is C, this is 2C, this is 2C, this is C. And we are supposed to find the C equivalent of this circuit. You can see the ratio from the left is 1/2, but from right is 2/1, right?
Yes.
So ratio is there, but it is inverted ratio, right? Isn't it?
Yeah.
And that is why it is called invert circuit. And this cannot be solved by the balanced Wheatstone bridge. Why? The cross
So
is
the
not
ratio
same.
is not same.
Yeah, it is 1/2, 2/1. So sometimes you may get confused and apply the Wheatstone bridge and get the answer. Be very happy because the option will be there. That is a trap. Okay. So in case of inverse circuit, the nature will preserve some symmetry, and let's try to understand this. Whatever will enter from here, if it divides into the ratio of Q1 and Q2, what inverse symmetry says that the same charge will flow in the other direction. Because if you remember the principle of superposition, if I change the polarity, the charge will reverse the direction, isn't it? So if the battery would have been this way, the charge would have gone here is Q1 and here Q2, isn't it?
Yes.
Yeah.
So if I reverse the battery, it will just go this way and this will this way. Correct? What does it mean is the same Q1 will come from here. So what goes here will come here, and what goes here will come here. Do you realize this?
Yes.
Yes.
And therefore, the middle branch will have some current, some charge, because the Q1 is coming, Q2 is going. So some might be either coming or going there. So you can choose whatever you want.
Yes.
And now see, if you do the charge distribution, everything will be conserved properly. So that is the beauty of the inverse circuit. It preserves the symmetricity, so it is easy to analyze such circuit. We can easily analyze the charge behavior, and we can also analyze a lot of other things we'll see just now. So the first thing, if I want to understand, is if you just ignore the terminal, because the terminal is A and B. So whenever it comes to the connection of a cell, I'll connect across this, right?
Yes.
So this question cannot be solved by the regular method. Yeah, of course we can apply the delta star, which will eventually give me the answer, but that is not our interest as of now. We want to solve by the circuit method. And in fact, circuit is more convenient, because the delta star will first you have to convert, and you have to deal with bad values of fractions and all. Okay. So first of all, how we solve question in which we have a circuit. So we connect a battery and we assume some charge from the battery called Q. And we know that every circuit can be replaced by one equivalent capacitor, because it's purely reducible, isn't it?
Yeah.
And because this is V, Q, so we can always write Q equals to C into V. So we can say the Q, the C equivalent we can write as Q by
V.
So we employ the Q by V method, like QV method, to get the C equivalent. So what we do is we hypothetically, if it is not given, we hypothetically connect a battery. We assume some charge flow, and by solving circuit, we try to get back the ratio. Okay. And once you get back the ratio, you get the C equivalent. The first step is clear, what we do and what we are supposed to do here. The second is we have to use the nodal analysis. So we generally use to solve inverse circuit, the nodal is the perfect way. Is this the only way? Answer is no. You can apply any. You can apply Kirchhoff's voltage law also to solve, which is tedious and cumbersome. This is tedious in the beginning if you're not solving much, but with some practice you will see that okay, this is really easy. Understood? Okay. So in the nodal analysis, what we do? The same trick. You remove the battery first. You assume the potential. So let's do it. Everyone, do it with me. So do it along with me, everyone. Then only you can learn. If you try to do at home, it will be more difficult. Okay, so first of all, what we do, we assume V here and 0 here. How many junctions we have? We have 2 junctions. And based on the number of junctions, we assume number of variables. So technically, we have to solve 2 equations. We have to apply KCL at X and KCL at Y. And the 2 set of equations will give you 2 answers, which you can solve and get the answer, isn't it? The other is, let's exploit the symmetry. We have realized that the potential across this point and this point is same as this and this, isn't it? Because we have same charge,
Yes.
same
Yeah,
capacitor.
yes, sir.
So using inverse symmetry, do we realize that V minus X is same as Y minus 0? Yes or no?
Yes.
Because both is equal to Q1 by C. Tell me guys, yes or no?
Yeah, yes.
Yes, sir.
So basically I can replace Y by V minus X, which will remove one of the variable, and therefore it is really convenient. So this is the circuit with only one variable, which is X. So how many KCL we need to write now? Just one.
One.
So just write it here and you're done. Can you take the effort of writing? Write KCL at X. I mean that junction. Tell me, and X is representing potential, right? If you remember the way we have done this before. So from X we have 3 capacitor connected, right? From X we have 3 capacitor connected,
Yes.
whose end potential now we have assigned, isn't it? So the end
Yes.
potential are how much? V0 and V minus X. Correct?
Yeah.
So can you solve for X, please, everyone? If you put some effort here, your circuit, you will have command over circuit. You can play with circuit. If not, you will struggle with circuit. Don't blame me later on.
So V by 2.
No. Do it carefully.
6V by 11.
That seems correct. I mean, something like that. Just check once again. So we can write X equals to how much? CV plus CV minus X plus 0, right? Upon 4C, correct? I can add the direct answer here. No?
Sir, but
See, just look at for
I
this
didn't
junction.
get
No. Don't say you didn't get. You have to think about it. For the given junction,
Huh.
can you look at the capacitor which are connected?
Yes.
Can you figure it out? What are the
Please
potential
connect.
of the end?
Yes, V.
So why it is difficult then? I know this is 0, this is V.
Yes. So for 2C it is 0. Yes. Okay.
So now is it easy to apply now? CV plus 2C 0
Yes,
plus
for
CV minus X
2V by.
upon 4C.
Yes.
Can you rearrange and get the answer?
2V
So
by.
4 CV. I think C is common, so I can remove the C also. So 4x equals to CV, 2CV.
2v by
So 2V minus x.
so 2v by 5.
2V by 5 is the right answer. Anyone getting the answer 2V by 5?
Yes. Got it.
Okay. So now if this is 2V by 5, you know everything. So
Yeah.
whatever the battery will send the charge, it is getting divided as Q1, Q2. And the same will come from the other side also, isn't it? So whatever will enter from this side, the same will come from this side. So can we write the Q as Q1 and Q2? Q is Q1 and Q2. And what is Q1? Can you find Q1? CV formula. Q1 is how much? Q1 is how much? Q1 is how much? Come on. Q1 is charge on the capacitor C. So C into potential difference, which is how much? V minus X.
Yeah. So,
Look at the left side here. And what is Q2? 2C into V minus X, right?
yeah.
Yes.
So we can add as CV minus CX plus 2X, which is CX. Am I right?
Yeah.
Yes.
It is V plus X. What is, by the way, V plus X? 2V by 5 plus V, right?
Yeah.
7V by
7V by.
7v by 5.
we are done. So what is C equivalent?
C by 5.
Yeah.
So this we could not have solved using the other method. It is the symmetry which will only help us solve. And this is the toughest part of this chapter. And now you can look at the question number 26. Can you see 26?
Yeah. 26A.
A part is not A. All four are based on same trick.
Oh, okay.
So the A is direct this question.
Yeah.
Understood?
Yes.
In B, you can actually remove the vertical line.
Yeah. 4-1.
All four will be removed. And what you're left with? And the middle you can remove, you can bring it down. So 1, 3 and 3, 1 becomes inverse circuit. It is like a superposition of two circuits, inverse and the rest capacitor. Do you realize
Yes.
this?
Yes.
Yes.
In the C option, the inverse is parallel with 4. Understood?
Mm,
The same ratio, 2 by 4, 4 by 8.
yeah. 2/4, 4.
Same.
Okay. Yeah.
No, it's directly 2 by 4.
But
Yeah,
here it is directly we
yeah,
can use
it is a balanced Wheatstone bridge.
Balance Wheatstone.
The 5 will be thrown out, right? Same ratio.
Yeah.
Yes.
So 5 you can throw, then rest will be easy to solve.
Yes.
And again, the D is balanced Wheatstone bridge. The top
Yeah.
bottom is, you can see top bottom.
Yes.
Yes.
Yes, it's the same.
It is just 6 gone.
And all 6 will be thrown out.
6. All 6 will
will
be
go.
gone.
So in the A, which is direct this question, B is you have to remove the 4 microfarad and solve the
Inverse.
the top 4 as inverse, and the middle one you can stretch below in
Yeah.
parallel. Okay. So you have to solve all 26 question, all 4 question. So now you can see the question 27. 27 we have done this. It's a purely reducible circuit.
Yes.
28 is the ladder problem. We have done this before.
Yes, infinite.
Yeah.
In 29 we have the ladder plus the last one. Ladder is eventually connected on the right side with C.
Yeah.
Understood?
So Millman.
Yes. So we
No,
can
not minimum. Just same. You have to first
Okay,
solve for
okay.
ladder
first ladder, then
and then connect with C and then think of how to get the answer without C.
Okay. Okay.
Then so you can do all. Now rest are simple, rest are series parallels. Come to the next page. I mean 30 onwards. So 30 onwards, it's a parallel plate question we have done before in the very first lecture, isn't
Yes.
it?
Yes.
We know how to find the electric field and how to write the things. Okay.
Yes. Yes.
So all questions are similar. Okay. We have also done the dielectric between the plate.
Yes.
Yes.
We have also done the induced charge. Okay. So you are supposed to solve all questions up to 62. So you start doing it. Yeah, 62.
Okay.
And there, the only one concept is left is the last three questions is a concept actually. So question number 66, 67, 68, and 65 I will teach in the next lecture, which is the last lecture. So this chapter will be thoroughly over. And now your duty is to solve one and each and every one question one by one. So don't leave a single question. This book is sufficient for Capacitor. This book is sufficient because anything which is not in the book I will be given in the theory lecture only. The rest you finish from this book. Okay.
Okay.
Once you are done with every question, then only go for something else if you have time. But first step is solve everything, including the objective 1 and 2.
Yes.
Yeah. So objective 1, objective 2, and then start the exercise. Questions are very easy. You can do it very fast. And I expect that you should be able to do it this in before the next lecture for sure. Everyone.
Yes.
Okay. So we are again meeting on Sunday. All right. For wave optics, see, I mean, there is a lot of clash happening for other students also. So probably I'll shift it either in the night if possible, or I'll wait for 1 or 2 weeks because I hope that you will be free from your classes. So,
Yeah.
I mean, once you're free from your classes, let me know. Then we can increase or, put more extra lectures as and when time required. Time is permitting us. All right. Bye and take care. See you in the next lecture. Your homework is clear?
Yes.
Yeah.
Finish before next lecture, else the current will put more burden to you.